Okay, don't forget to follow us on social media at Thinkable. Okay, the stream is going to have the rules for drawing Lewis diagrams, VSEPR shapes and the angles, hybridization, and the definitions and examples of sigma and pi bonds. Okay, so this is basics, and for sure you already know this. Lewis structures will represent the atom with its valence electrons. And the valence electrons, who can tell me which ones are the valence electrons? Where are valence electrons located? Excellent. Everything, yes, all good answers. The valence electrons are the ones located on the outermost shell. Great. And these ones are the responsible of making the chemical reactions, the chemical bonds with other atoms. So we represent them, as you already know, with dots around the symbol of the atom. And it's a common practice to use north, south, east, and west locations. So for example, here we have hydrogen, and here we have beryllium with its valence electrons. It's fine to place either the dots together, like in any of these locations, or to place it in opposite locations. So it would be fine as well to have north and south instead of east and north locations. Perfectly fine. And here we have other examples for boron, carbon, nitrogen, fluorine, helium, and neon. And notice how in carbon, I decided to place better the north, south, east, and west locations. And this is easier later it will help us for bonding. In nitrogen, I started pairing up and so on. Okay, when we do the Lewis structure for molecules, remember that covalent compounds and molecules are synonyms. So when we do this for molecules, the purpose of sharing is to complete the octet. In the case of hydrogen, it'll be fine because it will resemble helium. And the shared electrons, we can show them like this, or we can show them with a line. And one line equals 2 electrons. So we have here a single, a triple, and a double bond for hydrogen, nitrogen, and oxygen. Now, this guy here that is not involved in the bonding, it's called a lone pair. We can represent it in the Lewis structure like this, or we're choosing to place the lines for the bonded electrons. This is the lone pair. Okay, we're going to start with the steps for drawing proper Lewis structure for molecules. So the first thing that we have to do is to determine the total number of valence electrons. So for example, for water, we have 1 valence electrons for water times 2, since we have 2 atoms of hydrogen in the water molecule. And then we have only one atom of oxygen, so we multiply times 6. So we have a total of 6 valence electrons. Let's go to the next step. Determine the central atom. Usually it would be the one with most available sites for bonding. Which one do you think is the central atom here? Hydrogen or oxygen? Yes, Greta, Irene, Anna. Yes, you're right. Oxygen is the central atom. Very good. So we place the central atom and we draw a skeleton of the molecule. So this one here, it will help us decide the bonds, the ones that have more bonds for bonding. Here we have 2 sites for bonding versus hydrogen that has only 1 site for bonding. So that's how we decide if we're not sure. So then we do the skeleton of the molecule. And then right now, remember that one line represents how many electrons? Exactly, 2 electrons per line. So far we have 4 electrons shown. And remember that we needed 8. So what are we going to do? We're going to place all the remaining valence electrons to fill the octet. We're going to start with the most electronegative. Remember from periodic trends, which one will be more electronegative, oxygen or hydrogen? Remember the trend of electronegativity is a diagonal line on the periodic table, a diagonal line towards the top right corner. So if you remember the periodic table, you should notice that oxygen, correct, Irene? Oxygen is closer to the trend where electronegativity increases. So yes, oxygen is the one with the most electronegative. So that's where I'm going to place the rest of the electrons that are missing. So I place those and then I have 2, 4, 6, 8. I'm done. Then the next thing that you have to check is, are all the atoms fulfilling their octet? And you check oxygen has 2, 4, 6, 8. So yes. And hydrogen has 2. Is hydrogen fine with 2, or we need to add more electrons for hydrogen? It is fine with 2, correct? Because it resembles helium, the noble gas helium, and that's perfectly fine. Okay, let's do another example. When we do the same thing for polyatomic ions are a group of atoms that are bonded covalently but carry a charge. So for example, if we do the same thing for ammonium, we must consider the charge. So if we do the same that we did before for water, nitrogen has 5 valence electron times 1 because it's only one atom involved. Hydrogen has 1 valence electron times 4 because we have 4 in this formula. And then the positive charge, what does a positive charge mean? More electrons or less electrons? Paola, you're correct. Camila, yes, less electrons. So that's why we need to subtract 1 electron from the total sum, because a positive sign means 1 electron less. So we do now that we have the count, then we follow the same steps as before. Which one do you think will be the central atom here? Exactly, nitrogen. So we do the structure with the central atom. We count 2, 4, 6, 8. We already have all the electrons needed. And don't forget, if you're doing this for polyatomic ions, to place your structure between brackets and to place the charge. Don't forget the charge on the outside of the brackets. Questions? Not yet. Okay, we're going to move on. Okay, so let's do the same with NO3. Need to add 1 electron here. Come on, you know this. Negative charge. Electrons have what charge? Positive or negative? Ah, yes, sorry. I didn't notice the video got stuck. My question was, why do we need to add 1 here? Why do we need to add 1? Correct. Excellent, very good. Because there's a negative charge and electrons are negative, so we need to add one extra electron. Very good, thank you. So now our count is 24 valence electrons. We have to do everything with 24. Now, who can tell me which one is the central atom? Nitrogen, excellent. So we do the skeleton for the molecule. How many electrons we have so far in this skeleton? In the skeleton, correct. We have 6 so far. So we need to add more to complete the 24. Now, which one is more electronegative, nitrogen or oxygen? Excellent, very good. Oxygen is the more electronegative. So we start filling up the rest of the electrons, starting with the oxygen. So we have this, and now if you count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We already have the 24 electrons. Now we need to check if everybody fulfills the octet. So we check, and oxygens are fine. They all have 8. But what about nitrogen? Nitrogen only has 6. So nitrogen is sad. So what do? We are going to make multiple bonds. We're going to make a double bond. Oxygen, this oxygen is going to be very generous and is going to lend these 2 electrons to nitrogen. Now, by doing that, it creates a double bond. And this oxygen, it's fine because the shared electrons count for both atoms. So now we have 2, 4, 6, 8. Oxygen still has 8, but by sharing, it helped nitrogen have 2, 4, 6, 8. Now we have all 24 electrons accounted for and all the atoms ready with the octet. Don't forget to place in brackets and the negative charge. Questions? Okay, we're going to move on. Okay, so now we're going to consider exceptions of the octet rule. The second row, remember that we're doing this for molecules, so only covalent bonds. Just a quick reminder of which elements do covalent bonds. Exactly, very good. Non-metals are the elements that make covalent bonds. So we're going to consider only the non-metals. So the second row of the non-metals should be assumed to always obey the octet rule. And those are the examples that we have seen so far. Okay, now boron and beryllium, even though they're not totally considered non-metals, sometimes they create covalent bonds. And when they do, they usually have fewer than 8 valence electrons. These electron deficient compounds are very reactive. So this is an example of boron with chloride. I already did the count, 24 valence electrons. I already did the skeleton. So you add the electrons. And this is an exception of the octet rule. So we already have the 24 valence electrons, and boron is totally fine with 6 valence electrons instead of 8. So this is a proper structure for boron. Okay, another exception for the octet rule. Exactly. Boron is very agreeable. Thank you, Leslie. Okay, the second row elements will never have more than 8 valence electrons. Why? Because the second row elements, remember electron configuration? You can only have 2s and 2p orbitals on the second row. So there's no more space to accommodate more than 8. Okay, but the third row, and from the third row on, then these elements can exceed the octet. Why? Because they can use empty d orbitals to place these, to accommodate these extra electrons. So starting from row 3, then we can have exceptions of the octet rule where the central atom exceeds the octet. So let's see this example. If we have PCl5 and we need 40 valence electrons, we place all the valence electrons in chlorine because chlorine is more electronegative, and phosphorus forms an expanded octet by using these d orbitals. So it will have 2, 4, 6, 8, 10 electrons, and it's totally fine because of this. Now, with this information in mind, we're going to start with creating shapes, VSEPR shapes. VSEPR stands for valence shell electron pair repulsion. And it's just a method, a model that we use to predict the shape of individual molecules. So in here, it considers that the electron pairs would like to be as further away from each other because, as you know, electrons are negative, so they will repel to each other, trying to place, trying to be the furthest away from each other as possible. So, and we have to remember that the non-bonded, the lone pairs, will repel slightly more than bonded pairs. So with this in mind, we're going to start doing VSEPR structures. So the steps are to first do the proper Lewis structure with the steps that we saw before. And then we're going to focus our attention on the central atom. We're going to count the atoms bonded to the central atom, and we're going to consider also the lone pairs. And then we're going to decide the shape that will, considering that electrons repel each other. So we're going to consider what would be the furthest away possible that they can be, so they can have a spherical, geometrical, symmetric shape. Okay. So for example, carbon dioxide. If we do the count, we end up with 16 valence electrons. So if we consider the valence electrons for carbon and oxygen, we know that we find out that carbon has more bonding sites. So carbon will be our central atom. Then we do the structure, the skeletal structure, and we have 4 electrons so far. We complete placing more electrons with oxygen. And we notice that carbon is sad because it only has 4 electrons. So how do we arrange this? How do we fix this for carbon? What do we have to do? Very good, Camila. We force a double bond. We force a double bond by placing electrons from oxygen towards the bond of carbon. So this will help carbon without affecting oxygen. Now we have 2, 4, 6, 8 electrons for carbon. Carbon is very happy. And we have 2, 4, 6, 8 for each of the oxygens. So now all the electrons are accounted for and everybody is happy. So now, if we think of this in 3D, what will happen if carbon has only 2 atoms pulling from it? What shape do you think it will form in space? Okay, triangle, linear. Okay, so we're not sure yet, so let's see. So the central atom has 2 atoms bonded to it and 0 lone pairs. So the furthest away that they can be from each other, it's in a linear shape, right? So a linear shape will have 180 degree angle. And I have here I want to, sorry. Okay. I have here a model of carbon dioxide, central atom, and we have a double bond. And this is the furthest away it could be. Does it make sense to be linear? It does, right? That's the furthest away the atoms could be from each other, and there are pairs from each other. Make sense? Okay, we're going to continue with the, sorry. I didn't mean to do that. I want to go back to the other screen. Well, I'm going to move on, and maybe in a moment, Tan can help me place my image in the corner again. Okay, so we're going to move on with the presentation. Hover over the slides and click the focus tab. Thank you. Thank you, Tan. It's the first time that I do this on live, so okay, there, got it. Woo. Okay, let's move on. Excellent. Okay, let's move on. So carbon dioxide. Now we're going to see boron trichloride. If we do the same, we have to do the same with 24 valence electrons. Remember that boron is an exception of the octet rule, so it's fine with 6. So now the central atom has 3 atoms bonded to it and no lone pairs. So think about it in 3D. How would these molecules get organized so that everything is as furthest away from each other? Okay, we have pyramidal as an answer, trigonal. So let's see what boron does. Boron does this because that will be the furthest away possible. Right? Does it make sense? Now, I am going to try to do this again. I hope. Okay, so now, okay, so now this is the structure. And I place regular lines in the diagram. If I'm going to do the diagram by hand, then these ones are these ones right here. And if we notice, everything is on the same plane. So that's what these regular lines are showing. Okay, let's move on. Woo, I made it. Thank you. Okay, so CH4. CH4, it has a total of 8 valence electrons, and now we have 2, 4, 6, 8 valence electrons. Again, we have to think about this in 3 dimensions. How does this structure could get a shape where everything is away from each other? Cross pyramid? Okay, we have to think in 3 dimensions. Tetrahedron, great. Okay, all of these are great guesses. Tetrahedron is correct. Thank you, Irene. So we will have this structure, and if we draw it, we'll have this, and I'll show you the model in a second. Again, okay, here we go. So this is the model. I'm holding this line right here of the molecule, this one right here, it's a regular line because it's on the same axis as the paper, if you will like to think about it. The paper is right here. So this line and this line would be on the same plane as the paper. So we have regular line, regular line. Then this wedge right here is showing this line. So it goes forward to the front of the plane of the paper because we want to represent, what we're doing here is representing in 2 dimensions something that really exists in 3 dimensions. So we have a wedge here, and the dotted line will be the one that goes to the back of the paper, to the back of the plane. So I'm holding the 2 lines that are with regular lines. This is the wedge. This one is the dashed line. Make sense? Would you be able to do these diagrams on your own on paper? Sure, right? Yes, Stan, you will. You just need to practice. I'll help you. Okay, I am going to unfocus the screen. You can do it, Tan. Okay, we're going to move on. So tetrahedral shape, I forgot to mention the angle. This angle right here from hydrogen atom to hydrogen atom is 109.5. This is a very common structure. So for your AP exam, this one is something that you will like to memorize. It's very useful. Okay, let's move on. Okay, NH3. NH3 has 8 valence electrons. If we do the structure, we have it right here. Now we started having a lone pair. And remember that the lone pairs will do more repulsion to the molecule. So, exactly. So, okay, now we are going to have this kind of molecule. Let me show you. Let me show you right here. And I'm going to use again the model. Okay, imagine that this is NH3, but I don't have an atom here. I have a lone pair. So the lone pair, even though it's part of the carbon atom, it exhibits repulsion to the other 3. So that's why this angle is not 109.5 as before. The angle is 107.3 because it pushes them a little bit closer together. So we can have the model like this. This is the line on the same plane as the paper. We don't show the lone pair because it's actually part of the nitrogen atom. We have a wedge, this one right here, and shaded line or dotted line for the one on the back. We can have the molecule like this, or we already have models that omit the lone pair. And it makes sense since it's part of the nitrogen atom. Does this structure, does this model in 3D match or make sense with the shape on paper that we're going to do? Does it make sense to you? I am holding the regular line. The wedge is the hydrogen towards you, and the dotted line is the hydrogen towards the back of the paper. We're going to move on. Okay, excellent. If I can do these technological things, then you can do the drawings. Much, much easier. Okay, so water. Water has 8 valence electrons. Now we have this structure, and it has 2 lone pairs. 2 lone pairs, so what shape would water take? Remember, the lone pairs exhibit more repulsion. Bent shape, Greta, very good. So the lone pairs exhibit repulsion, and it will force the hydrogen atoms to be closer together. So it will remember that the lone pairs are actually part of oxygen. So it will look like something like this. Let me unshare the screen. Okay, so this one right here. Now, why do we have only regular lines on the molecule? On our diagram, if we do it on two dimensions on paper. Why only regular lines? We don't have wedge and dashed line anymore. Very good, Irene. Excellent. They are on the same plane as you will think of the paper, right? So we don't need wedges or dashed lines for this one, only regular lines. Okay, let's move on. Okay, so now here we have a summary of all the shapes that we have seen so far. These shapes are the most common ones, and I really, really think that you should memorize this. So it is actually very easy. Once you practice, you will have no problem at all. So if you have two atoms bonded to the central atom with 0 lone pairs, you will have a linear shape. And I have here examples for you. I will share the slides in the... I will share the slides for the replay so you can have these slides to study for later. So 3 and 0, trigonal planar, 4 and 0, tetrahedral, 3 and 1, trigonal pyramidal, and 2 and 2 bent. And those are the angles that are always asked for are the ones of tetrahedral and the ones of bent. Those for sure you will need to learn them. The one of bent is the one of water. Water is used a lot, and this bent structure helps them do its properties that are the properties for life as we know it. So it's very important to know at least those two angles. Of course, linear is very easy. It's obviously 120. So you only have 2 more to learn. So you can do this and you can memorize all this information. Any questions here? Camila, sorry, I didn't see your question. Does the shape affect the polarity of the molecule? Excellent, excellent question. Yes, actually the shape does affect the polarity. Do we remember what a polar molecule is? What does a polar molecule mean? A molecule that has different poles, positive and negative poles. Yes, Irene, correct. Camila, something that is charged positive and negative, correct. So something that has poles, as Irene is saying, like the Earth, north and south poles, like a magnet. And so we have, for example, that they are not close on the periodic table. Yes, Greta, considering the trend of electronegativity, it will be when the atoms are further apart from each other on the periodic table. Excellent, excellent answers. So for example, suppose that we have a dipole here. Suppose that this is partial negative, these outer atoms, and the central atom is partial positive. What do you think will happen? You have to think of this as vectors in physics. Imagine that this is one person and 2 friends are pulling from the arms. Do you think this person will move or it will stay in the same place if the central person is pulled from the sides? Exactly, the person will stay on the same place. It will stay stuck in place. Correct. So the polarities or the vectors will cancel out. So even though the electronegativity difference tells us that it will have a dipole, the polarity would get canceled because of its shape. So it will end up being a non-polar molecule because of this. So you have to consider the difference in electronegativity, but now also the shapes to determine polarity of a whole molecule. Questions? Yeah, right? Wow. This is something very interesting because now we have to consider the molecule as a whole. So this, I will give you a hint right now. This happens, the polarity will always cancel in case you have a difference in electronegativity when the molecule is symmetrical. So this will happen when it has 0 lone pairs on the central atom. So it makes sense, no? Because the vectors will cancel out if they're symmetrically distributed on the central atom. So non-polar, 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 regardless of the difference of electronegativity. Now, what will happen on these two? Do you think the vectors will cancel? Do you think one guy that is pulled by the arms, let me do this on a bigger screen. Do you think that if this was one person and two friends were pulling the central atom from here, do you think the person will be able to move or will stay put? Yes, if you're pulled like this, imagine pulling by your arms. Of course you will move. So if it moves, if the dipoles do not cancel, then the polarity of the molecule depends on the difference of electronegativity. The shape won't be able to cancel the poles in these kinds of shapes. And if you notice, these kinds of shapes do have lone pairs. So if you have lone pairs on the molecule, check the electronegativity because the shape won't cancel. Excellent question, Camila. Was that clear for everyone? Excellent. Good. Let's move on. Okay, let's move on to more shapes. Now, we're going to do some shapes of molecules that exceed the octet. Do we remember which row, starting in which row, we can have atoms exceeding the octet? Exactly. Starting on the third row. Slide. Yeah, Camila, great job. You're doing awesome. Okay, so, and everybody's with a really great answers. I am very, very happy to have all these correct answers tonight. Thank you. Okay, so yes, the elements on the third row will start having the opportunity to exceed the octet. Do we remember why? Exactly, because the ones of the third row can have more electrons. They don't only have the s and p orbitals, they do have d orbitals. So there's more space to accommodate extra electrons. Excellent. It's like if you have more rooms in your house, you can accommodate friends, but if you don't have more available room, you're not going to ask any friends. Excellent. So let's move on. So PCl5, 40 valence electrons, and this will be the shape. Now, I hope I have, yes, I do have one like this. Okay, so now, if we consider this molecule, the shape is going to be the trigonal Bipyramidal. Now, I am holding the lines. It makes sense that these three lines are on the same axis, on the same plane as the paper. So the shape will have these three lines with regular lines. This is your wedge. This is your dotted line. So 3D, 2D. 3D, 2D. Does it make sense? We have to learn to read this because in the book, we are not going to, the molecule won't pop out to us. We will see it in 2 dimensions. Excellent. Now this angle right here, the angle from here to here, it's a 90-degree angle, it's obvious. A right triangle can be drawn here. And the angle from this to this, that's 120 degrees. And the name of this shape is trigonal Bipyramidal. This one is achieved when the central atom has 5 atoms and 0 lone pairs. With this in mind, do you think this shape could cancel its polarity? Yes, excellent. This shape can also cancel its polarity because since it has 0 lone pairs, it can accommodate all its atoms in a symmetric shape, canceling the vectors caused by the dipoles. So yes, it will end up being a nonpolar molecule regardless of the difference in electronegativity. Okay. Let's move on. Okay, SF4 34 valence electrons. We are going to do the molecule and we're going to notice that sulfur will have more than an octet. It will have 10 valence electrons. Totally fine. So now we have 4 atoms bonded to it and 1 lone pair. This, if we consider the same shape as before, but we consider this strand to be a lone pair, then we will end up having this shape. And this shape, let me do the screen thing again. Okay, so we are going to have this molecule is the one that you have here. And actually, the one that I'm holding is a lone pair. So it will end up looking like this one. Okay? Now, how many wedges would we have for this molecule? Okay, let me organize. I'm going to remove this one. Let me organize this better. I am holding the ones that are supposedly to be on the paper plane. So how many wedges would it have? Excellent, excellent, Leslie, Irene. Yes, this will be a wedge right here. And this one will be a dotted line. So this will be our diagram. Regular, regular, wedge, and dotted line. This shape is called a seesaw. Doesn't look like a seesaw like this, but if we turn it like this, and then this game of the seesaw. Ah, sorry. I even draw here the children playing. Does it make sense, the seesaw shape? They're playing in the park. Okay, let's move on. So the seesaw has 1 lone pair. Remember that there's a lone pair here as a part of the sulfur. Do you think polarity will get canceled here? Exactly, no, this is not a symmetric molecule. So then what do we have to do to determine its overall polarity? What would we have to look for? Great, Leslie, you're on fire. Yes, we compare the electronegativity of the 2 atoms to check if they will have a overall polarity or not. Excellent. Okay, another example. This one right here has 28 valence electrons. And now we can see how chlorine expands the octet. We will end up having 3 atoms and 2 lone pairs. So again, if we consider the first shape, like this, trigonal Bipyramidal, and we consider these 2 to be the lone pairs and we remove them, we will end up with a shape that looks like this one. Now I'm going to remove this. These are the lone pairs, and they're actually part of the central atom of chlorine. Okay, so I'm going to remove this, and we're going to work with this one now. So now everything is on the same plane. So all regular lines now. Will the polarity cancel? Excellent. No, it won't be able to cancel. Excellent. Let's move on. So now this other molecule will have 22 valence electrons, and now we have three lone pairs. 3 lone pairs. So let's imagine that this one, and this one are the lone pairs. So they're actually part of the central atom. If we remove them, what shape would we have? Excellent, Irene. A linear shape. Excellent. A linear shape. Who can describe how we can do this on paper? How can we do this on 2 dimensions? Would we need regular lines, or we will need a wedge? Will we need a dotted line? Okay, Irene, 2 lines and regular, wedge, dotted. Exactly. No wedges, no dotted lines, because everything is on the same plane. Everything is on the same plane, and the angle is a 100-degree angle. Excellent. Now, will the polarities cancel? Think about vectors. Think about your physics background. Excellent. Yes, the vectors will cancel because electrons will pull away from the central molecule, canceling the dipoles. Make sense? Okay, thank you. Yes. Okay, so this is a chart that has the summary of all the molecules that contain the 5 electron pairs. So we have trigonal, bipyramidal, seesaw, remember the game of the children? T-shaped, it obviously looks like a T, and linear. So very easy to remember, very easy to memorize, to have this 5, 0, trigonal bipyramidal, 4, 1. And if you make sense of the diagrams, it will be very obvious for you. You just need to practice. And if you need examples, I place the example that we use for the video and 1 extra. Remember, I will share this presentation later for the replay, so you will have this right there for your notes. Questions? Okay, we're going to move on. Now we're going to see molecules with 6 electron pairs, and we have this one. Again, phosphorus is able to exceed the octet because it's in period 3. So this one will have 6 atoms bonded to it with 0 lone pairs. And using the model, this one is called an octahedron. An octahedron, which will look like this. Let me organize it as in the diagram. Okay, like this. So now, if we place it like this, okay, I'm going to hold the atoms that are intended to be on the same line as the paper. Okay, I'm going to tilt it so that you can see now, same line as the paper. So these ones are going to be regular lines. What are these 2 going to be if they're moving towards the front of the plane? If these are regular lines, what are these 2 going to be? Great job, Irene. Yes, these are going to be wedges, and these ones on the back are going to be dotted lines. So this is the diagram right here. We have a 90-degree angle from here and a 90-degree angle from here as well. Excellent. I'm not going to do all over all the molecules from these, but it's the same concept. Every time that you remove 1 atom and change it from a lone pair, you're just like removing pieces from this. So you can have the square pyramidal. If we remove this one, square pyramidal will look like this. And then the square planar would be if this one is a lone pair. So if we remove it from the model, square planar, and we can draw it like this. Any questions so far? Okay, we're going to move on. Okay, the next topic is hybridization. Hybridization means that the orbitals can hybridize or blend. I'm going to remove. I'm going to do this now. Sorry. Okay. Atoms hybridize their orbitals to have more flexibility in bonding. For example, if we do the regular electron configuration for carbon, that's what we will have. If carbon is able only to bond in this way, then it will be able to bond only with 2 atoms. And we know that that's not the case with carbon. Regularly, carbon, how many atoms does it bond with? The carbon atom. Excellent. Yes, it usually bonds with 4 atoms. So the way that carbon organizes to be able to do this is by hybridizing its orbitals. So, I'm sorry, here. So this is the regular one. Now, this one right here, this one of carbon, the arrow that is spinning in opposite direction, it's promoted. It's promoted to a 2p orbital. And now we have this on the bottom. Now we have space for 4 more electrons. Now carbon can bond with 4 atoms. So now when carbon bonds with 4 atoms, okay, we will have 1 s orbital, which as you remember, it's a sphere, the s orbital. And we have 3 p orbitals. Remember that these arrange in space on the x, on the y, and on the z axis. Now, if carbon stays with these orbitals, it wouldn't form a tetrahedron because it will bond somewhere here, the overlap, somewhere here, and somewhere here. So what carbon does is that it hybridizes its orbitals to distribute better around in 3D, to around the atom. So these 4 orbitals hybridize or blend. So I'm going to make an analogy here of placing this in a blender and then turn it on, and then we are going to get a hybrid, sp3 hybrid. S, only 1 S got in the blender, and 3 P's got in the blender. That's why this is labeled as sp3 hybrid. Thank you, Camila. Does this make sense, this hybridization? Excellent. So let's move on. Okay, so now if we remember, carbon forms a tetrahedron. It is able to do this because the hybrids now can be as furthest away from each other as possible. And that's how carbon bonds. Okay, carbon bonds with these hybrids, sp3 hybrids, every time it bonds with 4 different atoms. Now, if carbon has only the option to bond with 3 atoms, then this is what happens. This S electron, it's still hybridized to the p level. We still have 4 spaces for bonding, which that's what carbon wants because it wants to fulfill the octet. So this is what happens. But now the hybridization, the blender, only goes into the blender 1 s orbital and only 2 p's. 1 p orbital stays outside of the blender. It doesn't hybridize. So we end up with 3 sp2 hybrids. Why sp2? Because 1 s got in the blender and only 2 of the p's. And we stay with a pure p orbital. This one didn't get into the blender, so it stayed with its p condition or shape or whatever. So then this is what happens when carbon bonds with an sp2 hybridization. These ones in red are the hybrids. This one is the p orbital. So remember that this is one single orbital. So here they're circulating only 2 electrons that are bonded here. So this is 2 electrons, this is 2 electrons. We have a double bond right there. And we have, and this is the ethene molecule, C2H4. So now carbon is bonded with a hybrid and the s orbital of hydrogen, and it's bonded with the hybrids and with a p orbital. So if sp2 hybridization occurs, will there be 2 carbon atoms? Okay, Irene, great question. Not necessarily. This will bond whenever one carbon is bonded to 3 atoms. This carbon is bonded with 1, 2, 3 atoms. This atom could be different than carbon, not necessarily carbon. It could be oxygen. No, because it won't form this. Nitrogen, maybe. It could be nitrogen. I can't. You got me there, but not necessarily carbon. You can have other atoms different than carbon here. I used carbon because carbon is one that forms covalent bonds very easily. In fact, that's a whole section of chemistry that is called organic chemistry, which bonds carbon with carbon atoms. So that's the more common, Irene, but it could be a different atom. So the answer would be whenever carbon bonds with 3 different things, that's when it will hybridize with sp2 orbitals. That would be a more general generalization. So not necessarily this could be different than hydrogen and this could be different than carbon. Irene, did I answer your question? Excellent. Excellent, great question. Let's move on. Now, when we have a carbon molecule with a double bond, then the shape of the molecule will be trigonal planar. Why? Because we have 3 atoms bonded to the central atom and 0 lone pairs. So if you go back to the chart, that's what it would be, trigonal planar shape. Okay, let's move on. Now, when carbon bonds only with 2 atoms, then they still hybridize, but only at the s orbital hybridize and only one of the p orbitals go in the blender. So only one s and one p. So we have sp hybrids, only 1 and 1, and 2 pure p remain unhybridized. So I'm showing this with the green, pure p, and these are the hybrids. So whenever carbon bonds this way, this is what happens. I hope my diagram doesn't drive you crazy, but this is the carbon. The red ones are the hybrids. So the other carbon bonds first. This is the first one bond, and then the p orbital creates another bond above and below the plane. And then the other p surrounds that bond. And here we have the triple bond. One line for the red overlap, another line for the blue overlap, and another line for the green overlap. That will really, well, with imagination, but that it's what carbon will do for a triple bond. And it will form a regular bond here, a single bond with hydrogen. Questions here? Let me see if I can do a triple bond with my model very quickly. So I can show you this with the model. Maybe it will be more useful. if we do this. Okay. Okay. This is a triple bond, and we're going to have one bond that is not shown here, with the overlap of the hybridizations. And then we're going to have a bond above and below that will be one of the bonds created with the p orbital, and another one like wrapping from the side the carbon atoms. So we will have the 3 bonds right there. Does this make sense, or did I confuse you more? Yes? Okay. I hope I hope it's not too confusing. Okay. So, sorry. Okay. Now, lastly, we're going to see sigma and pi bonds. Sigma and pi bonds. Okay, the definition of a sigma bond is that it's one bond that is created with the overlap of similar orbitals, and the orbitals are aligned in the same axis as the nucleus of the atoms. So sp3 hybrid orbitals only form sigma bonds. Okay, and the form would be a tetrahedron. And pi bond is created when there is the overlap is not on the plane of the atoms. For a pi bond to exist, you must have a sigma first. So pi bonds will be created only when we have multiple bonds. So I'm going to use this as an example. This one will be a sigma bond because the overlap, which is this one, it's aligned on the same axis as the nucleus of both carbon atoms, sigma bond. This one right here is a sigma bond as well because the hydrogen atom and the carbon atom are aligned with the overlap. Does this make sense? So we have one sigma bond right here, one sigma bond right here, one sigma bond right here, and one and one. Now, this one, this is the overlap above and below the carbon atoms. Is the overlap, that is this one and this one, on the same plane as the nucleus of the carbon atoms? No, right? It's not on the same plane. It's not on the same plane. So this one, it's called the pi bond. Now we cannot form a pi bond. We must, without a sigma bond first. So that's why this is a double bond in C2H4. Does this make sense? I hope it does. Okay, let's move on. So another example of sigma in pi bonds, now with a triple bond. Okay. Is this overlap of the red orbital sigma or pi bond? Sigma, Irene, yes, correct. Because the overlap is on the same plane as the nucleus of the atoms. Now, what about this one? Will this be sigma or pi? This one right here, the overlap between carbon and hydrogen. Sigma or pi? Sigma again, correct, because again, it's on the same axis as the atoms. So we have sigma, sigma, and sigma. What about this blue one right here? The overlap takes place here and here. Are these overlaps on the same axis as the nucleus of the carbon atoms? No, correct. So these we have right here a pi bond right here. One. The Greek one, you can think of it as hugging, as placing your hands, hugging like this. The overlap is like your arms, like doing like this. So what do you think? Would this be a pi or a sigma bond, the green overlap? Excellent, Irene, great job. Pi again. So we have 1 sigma, 2 pi bonds when carbon does a triple bond. Do we have any questions? Great job, everybody. Excellent. Well, that's all from my part. If we don't have any questions, then you can watch the replay later. And remember, I'll place the slides for you. It will be useful to study later. Thank you. Great job. Awesome. Great answers during the whole stream. Bye-bye.